Next one is input vector control. Every circuit is an input vector with minimum leakage, right? So for example, right? So this is like in the class, right? Now madam is talking, so the students here are sleeping, right? Sleep. And then when madam asks question, they wake up. So here, this sleep signal is active when you are listening to the lecture. So for example, for the circuit, for the chip, the data, you also have a sleep vector. When it is necessary to, it is the opposite of the enable. So here, the sleep vector means that this marks right now, if the sleep is on, that means the marks is off, right? When the signal is active, you off the sleep vector and the data goes to the logic circuits and processes. So how do you implement this sleeping inside your circuit? You put in additional transistors here. Okay, so here is the logic gates, NAND gate, right? So when the sleep is active here, sleep bar is active. Okay, let's put here, sleep is active. So when sleep is high, right? Sleep is high, what happens to this PMOS? On or off? So you cannot sleep right now while I'm asking. Off, good. So when this is off, that means it is not connected to VDD and this signal is off. But when the sleep is low, the sleep is 0, this PMOS will turn on and this NAND gates will be pulled to VDD. So this NAND gates will be on. So when you can read this too, when the sleep is active, right? The stack effect additional of the transistor in the row to the other. Okay, so you can this is just a fancy thing. You can put the normal transistor for you guys, but sometimes people use high threshold transistor. Okay, but what you need to remember is that the sleep signal, usually you can see in your project, some of them they have used the sleep transistors. Okay, so you can put in the sleep transistor in order to switch off your logic cell. Okay, you can arrange them in a ring for your chip, right? So you put the sleep transistors in a ring, or you can put them in a grid, right? So everywhere the sleep, usually transistors have to be connected to the VDD. You can see here, the VDD is formed as the ring. All your other gates are in the middle here. And this one is like a grid. Your VDD is the grid. The VDD is like this, it is running like this and like this. Okay, so then you put your sleep transistors connected to the VDD in a grid form. Okay, the problem of the sleep transistor, right? The problem of the sleep transistor is that it will create an additional resistor, right? So in active mode, when the cell is working, there is a current through the sleep resistor. And there is a small voltage drop over the resistor. So your output voltage is not VDD, but will be reduced to VDD times X. So this sleep transistor is not without a cost. You will be reducing some voltage on your logic gate, and because of this, you will have lower performance, slightly lower performance. So this is why they like to put sleep transistors on blocks, on logic blocks that are not so active. Okay. All right. So this is the last slide for today, and then later we will continue. The power lecture is a bit long because we have a lot of techniques. Yeah, I am introducing a lot of low power techniques. Okay, So just to conclude, here lowering dynamic power, in what are the methods to lower the dynamic power? You have reduce VDD. When you reduce VDD, you have a quadratic effect, right? But when you reduce VDD, it has a negative effect on the performance, especially when the VDD becomes so low that it approaches 2 times the threshold voltage. Okay, lowering the capacitance also improve the minimum size. And how do you do this? By keeping the transistor in minimum size. And how else can you reduce the dynamic power is by reducing the switching activity. And this one, it is a function of the signal statistics and the clock rate. Okay, so you can do this by changing the logic, by introducing sleep transistors, by moving the logic blocks, reordering the logic, and all the other items that we mentioned today. Okay. Okay, so just to summarize, how can we reduce the dynamic power? You can reduce the dynamic power by reducing VDD. And because the formula is, this is the formula. See, this is the formula, CL times VDD squared multiplied by the activity. So CL, if you reduce VDD, you reduce a quadratic measure because the formula is VDD squared for dynamic power. Okay, so this has a negative effect on the performance, especially as VDD approaches 2V threshold. So if you reduce too much VDD, it will become very hard to turn on your transistor because you need to have sufficient voltage. The condition is that you must have higher voltage than the threshold voltage. Then only you can form the channel. But if you put in too low, then your channel will not turn on as quickly, right? So the other one is that you can lower the CL, the capacitive load. And how can you lower the CL? It is by keeping the transistor in minimum size. So if you reduce the C, you reduce the delay. So you will have, because the delay is considered tau is equal to R times C. So you will improve the performance. Okay, the other method, the final method is to reduce the switching activity, which is the frequency. How do you reduce the switching activity? You can reorder the signals, like what we did explain last week. You reorder the signals and you change the clock rate. This is depend on the logic and the architecture. Okay, so this is the dynamic power. That is the middle green is the short circuit power. Short circuit power is a function of the short circuit current, I peak, the time where it short circuit, T short circuit, and the frequency of switching. And finally, there is the leakage current. Okay, so now we look on the impact of the capacitive load on the short circuit current. So the capacitive load, if you have a large capacitive load here, so as you know here, the delay tau is equals to R times C. So if you have a large capacitive load, higher C, we will have higher delay, right? If C is large because it's proportional, so your output fall time will be significantly larger than the input rise time. Okay, so you learned about how to measure the fall time, right? So you know this means that your circuit will be delayed and your fall time will be larger. Okay, of course the reverse is true. If you have a small capacitive load, the tau will be reduced, so the fall time will be smaller than the input rise time. So this is the impact of the capacitive load. Where is the capacitive load? It is between the output of the transistor. Okay, how is it capacitive load formed? It is dependent on the size of your transistor. So if you have bigger transistor, you have higher capacitive load. Okay, so I peak versus capacitive load. All right, so when capacitive load is small, I peak is large, right? So you can see here, PL, it is inversely proportional. Because when you have a lower load, more current can pass through. So this is CL, this is the capacitive load, 20 femtofarad. Okay. If you increase the capacitive load here, 500 femtofarad, you see that the value of the I peak has been reduced from about 0.2 milliampere to 0.05 milliampere. Okay. Short circuit dissipation is minimized by matching the rise and fall times of the input and output signal, or slope engineering. So how do you match the rise and fall time of the input and the output signal? Okay, so if you remember when you did your inverter, right? You have your inverter. You have your inverter. How do you determine the size of your PMOS and your NMOS? Anybody? Okay, so let's say mu n equals to 2 mu p. All right, so let's say this size is 3 over 0.6. What is the size of the PMOS transistor? Anyone? Guys, you want me to call someone? Anybody wants to volunteer?
6 over 0.6.
Yes, good. It's 6 by 0.6. Okay, so why do you make it bigger? Why do you make it 6 over 0.6?
Because PMOS is lower.
The mobility is lower. When the mobility is lower, what happens if we don't make the size the same? So let's say you have your input. This is, we did the waveform, right? We checked the waveform in the lab. Let's change color. Okay. So this is the waveform of the input, for example. Okay. What the waveform of the output should be like this. You saw in your ring oscillator, the output is the inverse. Okay. So what happens if you do not make this, you do not make the current equal? Or maybe I should ask a different question. Where is rise time? Rise time. Where do you think is rise time? And where is fall time? Anyone? Let's ask who next. Mirza, what do you think is rise time?
The rise time is from the low to the high voltage.
Yes, correct. So from 0 to 1 is the rise time, from it going from 0 to 1. What about
Yes.
fall time?
From 1 to 0.
Yes, fall time is from 1 to 0. So here, if you want to measure the rise time, right, this guy will, this one, because it has the slope is going down, it will cause the output to go up, right? This will be the rise time. Okay, here, from here, this point to this point. So this is known as the rise time. And the fall time, oh wait, let me just check. Is that the rise time? The rise time should be Okay, sorry guys. The rise time is the time for it to go up. So it should go from here to here, from 0 to 1, and the fall time is going from 1 to 0. So this is TF. So when you rise time, when you want to pull up, which transistor is active, PMOS or NMOS for the rise time? Your rise time, you're going to pull it up to 1. So which transistor is active?
PMOS.
PMOS, good. So this will be controlled by the PMOS, and the fall time will be controlled by the NMOS, right? So if you have the capacitive load, the size of the transistor at the PMOS is not double, then the current for the pull up will be slow, right? So the rise time will not be matching. So what do you mean by rise time not be matching? So this is the rise time. If it's the rise time is slow and the fall time is fast. So you can see here the rise time here. By the way, this is T and this is voltage, right? Voltage. Okay, so this is the rise time. So you can see here the rise time is not matching the fall time. Here the fall time is short, but the rise time is long. This will happen if you do not size this to be double. If you make it 3 over 0.6, then the rise time will be slow. So if you want it to matching rise time, that means TR equals to TF. This is where when you scale the transistors. Okay? Any question? Everybody okay? All right. So now P short circuit as a function of rise and fall time. Right? So as you can see, look at the graph. If you can see here, when the VDD is high, VDD is 3.3, the power is high. When VDD is reduced, the power is reduced. Okay? So as you reduce the VDD, you can see that the normalized power will be reduced. Okay, so now we look here, when the load capacitance is small, the power is dominated by short circuit power. Okay, so the load capacitance is small when you have already done the matching, and this power is dominated by the short circuit power. All right. So, but if you manage to put VDD less than V threshold of N plus V threshold of P, then the short circuit power is eliminated since both of the devices are never on at the same time. Okay, so how do we do that? We will look at the voltage here. The voltage here, you will put in the voltage, set the VDD to be less than V threshold plus VTN, then P short circuit is eliminated because both of the devices are never on at the same time. So if you put the lower voltage, then you can eliminate the short circuit current. But if you put too low voltage, then you will have large delay. So there is a trade-off on this. Okay, so this one are the details about the circuit. W over LP was 1.125 micron over 0.25, and W over LN is 0.375. So this one is slightly more than double. It depends on the technology. So you can have the ratio to be slightly more than double or double. It depends on the technology or the foundry. All right. Okay. So the summary, short circuit power is consumed by each transition, increases with input transition time. Okay, reduction requires the gate output transition should not be faster than the input transition, or the output, the fall time should not be faster than the input time, the rise time. Okay, so you want it to be equal. Increasing output load capacitance reduces short circuit power, and scaling down the supply voltage with respect to threshold voltage reduces the short circuit power. So if we look at the equation here, it is T short circuit VDD, I peak, and frequency. So if you reduce the activity, you can reduce the short circuit power. If you reduce the peak current, this is by reducing the load, you can reduce. And you reduce the VDD, of course, you will reduce the power. And you reduce the time that both transistors are on. This, you can also reduce the short circuit.